Hello. Alright, we're just going to see if this works, and we're just going to do a quick speed proof of. I'll write out the theorem as what we're going to prove, then so afterwards describe in like simple words what's going on. I say simple words, like simple-ish, I don't know, we just do a thing, you know. Alright, so we got a theorem. Ooh. This is an unstable. There we go, this is stable. Okay, so our theorem we're going to prove is we're going to have, to write out the theorem, we're going to let v equal reals to power n. We're going to let w equals real to the n also, but without the zero vector. And then we have the n is of the naturals, but not including 0 or 1. Alright. Can I go to the left? Can't go that way for some reason. There we go. Alright, so those are our first things that we'd define to exist. We'll zoom out a little bit. And then we're going to let pi, which is going to be our n-1 dimensional hyperplane, we're going to say let that be vector v of v such that v dot n equals d, with n being of the set, n is going to be our normal vector, it's going to be of the set w, because normal vectors can't be the zero vector, and then we're going to have d of the set of reals. Then the zero vector of n dimensions, I guess it's clear there, but here I'm going to write it. Then 0 of n is of the set of pi, if and only if d equals 0 inside of pi's definition. Maybe a little unclear, but yeah. So the idea is 4 equations of the form v dot n. Oh, out of convention they tend to use r. Let's use r. It's better to follow the conventions, and then it'll look more normal. There's no reason we can't use v, but r is clearer, so we'll do that. Then r dot n equals d. So 0n being of that implies that d equals 0. So there are two ways to this proof, obviously, because it's an if and only if proof. So which direction's easier to prove is the question. We'll do the... Oh, I should name these statements as well. So maybe let this be 1, or let this be 2. Oh, they're quite simple, so I could probably write out, but this will make it easier to think about. So I think, given that it's off the point that implies d equals 0 is easier, so we'll do that proof first, and then we'll do the reverse direction afterwards. So the 1 to 2 direction, which is 0n being of this plane, implies that d equals 0. Let's do it. Since 0n of the set pi implies when r equals 0 and r dot n holds true. Alright. Oh, I've been staying like a million miles away from the microphone, sorry about that. So we got since 0 is of pi implies r equals 0. When r equals 0, r dot n. Oh wait, I need to put equals d holds true. Equals d holds true. But for any n of the set w r dot. But for any n of w, yeah, I'll put r dot n equals 0 for r equals 0 n. Implies that 0n of pi implies d equals 0 as required. I do like to do a little half. Maybe we'll do a half for this proof, because we've done one direction, and then when we've finished the proof for the other direction, we'll put a full square to say we finished the proof. Alright, so now we've got to do the other way, which is a little bit trickier. That always tends to be the case, is that one direction is a little bit harder than the other case. 2 implies 1, that means that d equals 0, implies that 0 is of the set of pi. Alright, let's look at that proof. So we'll say let r equal x1, x2, xn of the set V. Let n equal, what should I call the elements? I can call them u. That's, maybe it's confusing. No, you know what, I don't care. We're doing u. u2, un of the set of w. Pi's definition gives for r of the set pi, r satisfies I just realized we need to say we have it is true that d equals 0 always. For this direction of the proof. There's more words than I maybe needed, but I prefer to have it more clear than less clear. So we have it, it's true that d equals 0 always for this direction of the proof. Let r equal that, let n equal that. Pi's definition gives satisfies. In this case, we already have d, so we have that r dot n equals 0. And this is directly equivalent to, from our definitions of r and n, we've just defined a second ago, we have that this is equal to x1 u1 plus x2 u2 dot 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 xn un equals 0. A system, no, a homogeneous, there's a little another e here, homogeneous system of linear of one linear equation in how many unknowns? In n unknowns. Okay. And we can just put directly this implies, because homogeneous systems always have the x1 equals x2 equals xn equals 0 solution, so we have implies Wait, we'll give this a number as well, so we'll call this 1.1. Implies x1 equals x2 equals etc. equals xn equals 0 is a solution of 1.1. Implies that the 0 vector, does it? No, it implies r equals 0 and is of the set pi. It implies that d equals 0, implies that 0n is of the set pi, which is an n-1 dimensional hyperplane. Alright, and that concludes. How long did that take me? That was a pretty fun proof, I'm not gonna lie. I don't know if that was much fun to watch or not. I don't know, I didn't really explain myself so well, but I thought that was pretty legit. This is a nice little linear algebra proof we've got going here. This is the kind of result you can take for granted, but it's nice to see a rigorous proof. And this works for however many dimensions you want, and it's just a useful fact that when it's in this form, if d equals 0, then the plane contains the origin. That's an if and only if. So if this isn't 0, that means that the plane will not contain the origin, which is a useful fact as well. Perhaps more useful than this, but it's just generally a useful proof to have under your belt, so glad I could get this one done. Alright, see you, bye!